speaker in this symposium is Vassilevski, also from the Shemyakin-Ovchinnikov Institute. And you announce your lecture yourself in English. Victor is translating.
Well, I have a pleasure to translate. He's one of the quite active scientists, young scientists. And apparently, you will see, apparently he's not a bad English.
No, he's
Okay. Right.
He's talking about what?
Yeah, now we translate it together with Ferdinand. This is spider toxins acting on potential sensitive sodium channel, unexpected diversity, and possible practical application.
Oh yeah, wonderful.
All right, so I shall start with thanking the organizers and in particular Professor Zetman for inviting me. I'm really flattered. And so I will carry on with Victor Zetman's trend, and will try to talk to you about some things venomous. In this slide you can see two pictures which underlie things that we're interested in. So this is the front entrance to the Shemyakin-Ovchinnikov Institute, and you can spot valinomycin there. So that gives you the idea that we are into selective membrane transport. And then there's, although it's shrinked, as with other speakers today, so this is the logo of my group, and you can tell that we are interested in the nervous system, and then we are interested in venomous creatures, and trying to use toxins to see how nervous system is organized and how propagates signals. I will focus on spiders in this talk, and I will further focus on a particular group of spider toxins that affect voltage-gated sodium channels. All right, yeah, it's there's a little retard, but okay. So we are surrounded by a world of toxins. And people are usually afraid of venomous stuff, but I will try to convince you that this is not only a world of wonder, but actually a world of biochemical wonder. So there's the animal tree of life, and you can see that it is all scattered by venomous creatures. And there are the spiders, the champions of venomous world in terms of the complexity of their venom and the overall compositions, the variability of the toxins that we find. Often toxins target the nervous system, and moreover they find some, let's say, focal points in the nervous system that they affect. So these are the axonal membrane, then the neuroexocytosis machinery, and the postsynaptic membrane. So here are the postsynaptic ligand-gated ion channels that we have had several talks about today. So those are ligand-gated ion channels. But in the axonal membrane, the channels are voltage-gated, and so you can see several toxins, several hero toxins that are known to affect those guys. So sodium channels, the rising phase of the action potential, and potassium channels, the falling phase of the action potential. All right. So because so many venomous creatures produce toxins that affect the axonal membrane, it seems that sodium channels are in fact a focal point of neurotoxin action. And indeed, if we consider some vicious creatures, some deadly stuff, so scorpions and those deadly Australian and American spiders, we shall see that the major weapon of those creatures are toxins that affect sodium channels, and they are sodium channel activators. You can also see that the structure of those toxins is rather simple. They are peptides. They're very stable peptides, so many disulfide bonds that stabilize the structure. So once again, the major weapon of some vicious creatures are toxins that activate sodium channels. What do we expect when we inject a toxin that activates sodium channels into an animal? We actually expect excitation, and indeed in the urine, we'll see if it works. I hope it will. No, as with the other speakers today, we have this problem with video stuff.
Don't complain, please.
But anyways,
Click
no
twice.
complaints, no complaints.
Click twice.
So you see, click twice over
By mouth.
by the mouse. No, but the mouse doesn't work. Oh, it's a mouse. Get the mouse.
That's it.
Yeah.
Anna.
Click this button. No, but
You and mouse, you are
But anyways, that was a nice video which was showing you a toxin being injected directly into this mouse brain, and that was an activator of a sodium channel, and then the mouse just went wild. So indeed, if what you expect is activation, and this is indeed what you see in a urine, in a simple urine model. Okay. In that case, sodium channel blockers can be remedies to venomous animal bites. And indeed, I will show you a couple of examples where this idea works. So this pretty beast, red beast there, is an inhabitant in Central Africa. And although it seems pretty to me, local tribes are scared of it as hell. And in fact, if we consider co-evolution between primates and spiders, it might tell you that the current arachnophobia in many people, well, I have many arachnophobic friends who are so much afraid of these creatures that they won't enter a room if they just know that there's a spider somewhere. So this tells you that indeed it might be inherent. This arachnophobia might be inherent. There's an evolutionary reason to that. I put a smiling face down there because this is some kind of a folk theory, yet with snakes we know that it works. The co-evolution of snakes and primates is well documented. So, okay, this beast, if we inject the venom, and again I have a very nice video, you will see that again in the murine model you see activation, you see seizures and cramps and all sorts of jerks. So you expect that a major component of that venom is again a sodium channel activator. Another nice creature here produces, so this one inhabits India and Sri Lanka, and it lives in palm trees. And so if someone climbs those palm trees and disturbs the spider, it attacks. And then the cramps and seizures in people will last for days, weeks, or even months. And again, the symptoms show that perhaps it is a sodium channel activator. All right, in that case, let's test several kinds of treatments. So we selected those pharmacological substances that are available, freely available through pharmacies. We tested those in the urine model, and what we see is that in fact a sodium channel blocker is the best remedy to the venom. So the simple logic works. The major component of certain venoms are sodium channel activators, and then to cure the symptoms you need a sodium channel blocker. Moreover, sodium channel toxins present market variability. So here's a simple scheme illustrating the possible states, the states that the channel assumes: a closed state, the open state, and an activated state, and all sorts of transitions. And it seems that there are toxins that modify all of those possible states. So here's a scheme shared by Dillon. We indeed see that there are toxins that just block the current through blocking the pore of the channel. We know that there are certain toxins that shift the activation of the channel, and we know that there are certain toxins that affect the inactivation of sodium channels. And all sorts of toxins can be found in spider venom. And different toxins affect different binding sites. So this is a model of sodium channel structure. There is none available yet of a eukaryotic sodium channel. But we know how it should look like: a pore, central pore domain, and then 4 voltage sensing domains. And so the pore blockers bind to the pore, and then different modifiers, gating modifiers, bind to different voltage sensing domains to produce the different effects. And again, in spiders, you find all kinds of toxins. Moreover, we can find in spider venom toxins that present marked specificity, taxon specificity. Consider this spider here, Agilena. So it produces toxins that well affect insect channels. So again, there's the profound inhibition of inactivation, but these toxins are totally inactive in mammals. So no activity on mammalian sodium channels. And we believe that these types of toxin can lead to new insecticides. And finally, the final example that we'll try to tell you about is that certain sodium channel toxins found in spider venom are considered currently as hits for channelopathy therapy. So here's a famous scheme by Kenton Schwartz telling you that the voltage sensing domain is a domain senso stricto, so it's found in voltage gated channels. It is also found in voltage gated enzymes and by itself. So there are voltage sensing domains that act as channels, protein channels, and all of those are related proteins. So we can imagine that by a small number of modifications, of changes in this domain here, we can produce something like this. So if we modify, just introduce several changes into a voltage sensing domain of a voltage gated channel, we can see current through here. And this is indeed what happens in certain pathologies. So there are several pathologies. One of the important ones is hyperkalemic periodic paralysis, and this is exactly what happens. So certain mutations into the voltage sensing domain here produce the additional current that is called omega current. So the major current through the pore domain is alpha current, and this is the omega current. And so this is the molecular basis of the disease. And these diseases are currently considered undruggable. How do we, what do we do? So we, once again, turn to the variability of toxins. And we know that there are toxins that bind exactly to those domains where this abnormal current runs through. So we tested several toxins of that kind and found a spider toxin, so its structure was determined by Zakhar Shemyakin-Ovchinnikov, our speaker this evening. And you see that, so we tested it on the omega current, and you see that it blocks the omega currents. And we tested it on those channels that are the exact channels that are expressed in those pathologies. So these were isolated clones from patients expressed, and then the toxin was tested. And we believe this is the way to push and try to propose a remedy to those pathologies. All right, so I will conclude here with take-home messages. Sodium channel toxins from spider verms are very diverse, all kinds of blockers, eating modifiers. We find insect-specific, highly insect-specific toxins in spiders that can be perhaps used as safe bioinsecticides. And the last, but not least, some toxins are believed to represent hits for channelopathies. I will acknowledge many people from the Shemyakin Institute, but also from Moscow State University, from the University of Leuven, and University College London. This is my charming group, and I take this chance to pay tribute to Professor Grisham, who initiated the work and who was truly a champion of toxin research worldwide, and who will be remembered as long as his school, his legacy survives. And I thank you for your attention.
Thank you very much. Let's drop one brief question from my side. This going wild of the mouse after injection, could it just be related to pain?
No, it goes directly into the brain, so it doesn't hurt. And then there's a control mouse where we inject saline, pure saline, without toxin, no effect. So of course it's a controlled experiment.
Okay, further questions?
Is there a big sequence variability between different toxins? Because they are different from groups, and this is a question about transition.
Right, so the variability is very high. If you compare spider toxins and, let's say, scorpion toxins that are known to bind to the same site of the same channel, you will see that the folds are different, so the sequences are totally different. But if you compare different toxins from one spider, you will see that the disulfide bridges, so the cysteine residues, are fully conserved. They are present, but all other residues are very high variable. So this is how it is.
What about the structural similarity to the chronotoxins that block sodium channels? Is this a totally different class, or are they comparable?
The chronotoxins that block sodium channels, they are mu chronotoxins. And then there are also those that activate delta chronotoxins. Mu chronotoxins are pore blockers, but the folding pattern and the sequence is totally unrelated to spider toxins that block sodium channels. And delta chronotoxins are unrelated to scorpion toxins that activate sodium channels. So no homology between those.
One more question. Do your toxins also act on calcium channels?
Right, so there are...
I'm sorry.
Okay, thank you very much.
There is a huge variability of spider toxins. I was referring today only to those that affect sodium channels.
And the ones that do affect sodium channels, do they also block calcium channels?
Oh, those ones that, right.
Yeah.
So there are spider toxins that do affect the calcium channels specifically, but those toxins that I was showing, they are not active on calcium channels. They are specific to sodium channels. But also there are certain toxins that are, let's say, promiscuous. So certain toxins do affect voltage-gated sodium channels, voltage-gated potassium channels, voltage-gated calcium channels at the same time.
The reason I'm asking is because you can actually mutate the sodium channel, make it into a calcium channel by a single mutation, by a point mutation. So one would expect those to be blocked then, right?
Right, so if you mutate the selectivity filter, exactly, you can turn a calcium channel into a sodium channel and vice versa, but those, so the pore blockers, the peptide pore blockers, they don't actually reach it seems that they don't reach the selectivity filter. They bind a little bit further up in the channel turret, so they don't reach exactly the selectivity filter. So by introducing mutations there, you don't really change the toxin selectivity. Right.
Thank you very much. No, I'm afraid we have to stop. Our organizer would like to have some concluding remarks.
Yeah, think about the concluding remarks will be on behalf of our boss. We're together. Well, first of all, I'm really thankful to all speakers who came, who survived some minor technical problems, and they gave excellent talks. And also, I really want to give my thanks to Pierre-Jean and Margot, because last year, in the frames of American Neurochemical Society, I was organizing a symposium on cis-loop receptor. I invited them, I invited Yakin, another American, quite a good person. And to tell you, so between us, secretly, the audience was not as full as it is now. So I'm really grateful to our scientists who are sitting here, who survived all these and all the guests, and in particular, I'm grateful to Israel Silman, who is quite some years as me, some many years as me in cholinergic field, and he made some corrections to my slide because, well, it's not understood that I couldn't put a long reference of this journal which does not exist for many, many years. But he's absolutely correct, and he stressed really important features because I was trying to give you also a historical remarks and a sort of, as I put it mildly, toxin receptor archaic music. So once again, many, many thanks to you, and I'm happy that we're already here 6 minutes more, and Sikashvili didn't come and didn't tell us the room should be free. Thank you very much, all of you.